Right, so we back to continuing our lectures and so on. Yes, I'm in the process of marking the midterms. I'll just try to make a start on everything. And so it'll give me a little while. It's just, I have no assistants to mark these things. So I'll be doing it myself. So it'll take me a few days to get through everything. And then someone asked a question too about whether you'll be getting back the papers as well. Yes, you will be getting them back. I'll upload them once I'm finished marking, I'll put them back up for you to see and to see any comments that I made on them. The thing about it is that marking these things now is a little bit more tedious because marking, it's easier to mark paper, believe it or not. Where when I have something in front of me, it's easier to go back and forth and mark it. But here it's electronic, so marking it in a PDF, I find is just a little more cumbersome. But anyway, we will get that, and we'll have time to go through that as well as part of our revision and to clarify any things that may be still giving people issues. Yeah? So let us start today. Good luck at 100+ papers. Let me see, 80 and is 100 and is a little over 150. So we still have a way, little way to go. Teachers work hard, you know. Okay, so let's continue here. When we last ended, something like those soap opera TV shows. When we ended last, we were talking about the Fourier transform, and we had looked at the properties of them, especially the properties of certain of the test signals that we use a lot, which were the impulse, and we saw that the Fourier transform of an impulse was essentially a very flat, infinite frequency signal, which is why it was such a critical test to perform on a system. And basically, when you put an impulse into a system, what you were doing was to subject the system to a phenomenally wide range of frequencies coming into it. The other signal that we looked at was, of course, the unit step. We saw that the unit step had two things where when you started to look at the unit step in the frequency domain, and remember that's a little distinction here that when we talk about the unit step in the time domain, we talk about things like it being a causal signal, you know, nothing before, nothing less than t equal to 0, and then 1 afterwards. So you have this idea that it goes from 0 to, you know, some positive value. But when you look at it in the from another perspective, which happens to be the frequency components of it, we see that that sudden change has a DC component that is half the value of the step, whatever the value of the step happens to be. If it's a unit step, of course, it's just exactly half. And then there's the other side of it, which is the frequency spectrum, which is a decaying exponential kind of spectrum. But that sudden change gives us an impulse right at DC. So that when you put a step onto a system, you subject it to an impulse right at DC, and then you have this decaying sort of frequency response going forward. And then you were left to figure out what was the spectrum of a sinusoid. I think that was the last example, and to do and think about that. And it's very straightforward if you think about it in terms of the properties of the Fourier transform and what a sinusoid is in frequency. A single sinusoid has one component in frequency. So if you remember that, and the properties of the Fourier transform, and I told you already to use Euler's relationship between sine and e to the j omega t, you would be able to figure out exactly what the answer was. All right, so that's still there, and we'll talk about that maybe in the next tutorial that we meet, or when we're doing any revision a little bit later on. So up at this point in time, we have a sort of mini table of what we have come up with so far, which is like what you know from the Laplace transforms, right? So all of these things people go through and would develop all of the from the signals that you have, what exactly are they? the Fourier transforms of the types of signals that you're going to deal with. And there are many around the place, so that you don't have to go over and basically reinvent the wheel. But some of them you should know by heart. So and we went through the ones like the what do you call it? The impulse. We spoke about that, right? This one, this particular one, these two actually came about together. That we saw that an impulse in time gave you a 1 in frequency, and a one or if you like a constant in time give you an impulse in frequency. So that's the thing. You would have met it maybe in your digital electronics, something called duality. All right. So an impulse in time translates into a constant in frequency. An impulse in frequency inverse transforms to a constant in time. And because of that, we were able to derive the Fourier transform of a step, which gave us a combination of a sort of a hyperbolic kind of decaying frequency response and an impulse as well. Okay, and then we saw if you wanted to make a practical impulse, well, the closest that we get to that is a very narrow, very tall pulse that we could do this particular one, and that gave us this kind of behavior in frequency that we call the sinc function. And that is something that will come up time and again here and in other courses as well. And the sinc function, of course, looks like this. Sorry, the line is supposed to go there. It's going up and down, up and down, up and down. All right. The magnitude is 1. Right, and it has some zero crossings here depending on multiples of a over 2. Okay, and what we saw is that if we made a very small, that these points here, the zero crossing points, moved further and further apart, and eventually when a was 0 and the pulse became an ideal impulse, then the spectrum flattened out to become the constant in frequency. All right, so that behavior, you need to remember that. It's going to come up a lot, and I'll mention this a little bit later on when we talking as we continue with our discussion on filters later on this evening. Just a little bit about that comment on the sinc spectrum, right? Just to keep in mind. All right, and then what we had derived, of course, an exponent e to the minus at gave us 1 over a plus j omega here. And this is almost straight from your Laplace transform. You could substitute the s equal j omega. At t e to the minus at gives us, of course, a quadratic below. And then the sinusoid gives us this. Right, this was where the last the problem that I told you to work on, and instead of a cosine, it's a sine. But basically, what this looks like, if I ask you to draw this, right, delta omega minus omega naught is what? What does that look like? Delta omega minus omega naught is what? Yeah, I know the coffee hasn't soaked in, especially for those of you who are 1 hour behind us. But delta omega minus omega naught is what? An impulse where? Right, shifted to the right, good. An impulse centered on omega 0, correct. Right, so delta omega minus omega 0 is an impulse here at omega 0. And of course, delta omega plus omega 0 is an impulse at here. Right, so that the Fourier transform of cosine omega naught t, right, and cosine omega naught t, of course, is this function, right? It starts at 1 and so on. When you look at that, this is time. And when you look at that in frequency, right? You see that the spectrum, remember the Fourier transform is a spectrum. The spectrum of this is a frequency at omega. And of course, when we have minus omega naught, because remember we're dealing with complex numbers, so it has a real and an imaginary part to it. And this is what I was telling you is instinctive, should be intuitive, that the one below, the cosine omega naught t, has a single frequency component at omega 0. So therefore, the spectrum will have a single frequency component, which is at omega 0. But because we are dealing with the complex numbers, and we mentioned that already, that in order for the mathematics to be correct, we plot it as omega and minus omega 0, right? And that is because of the fact that the Fourier transform has a e to the minus j omega in the integral, right? That j is going to create a complex conjugate, so it must have a real, a positive and a negative in order for it to work out, right? And pi, of course, is the weighting. So the height of this, the height of the impulse is pi, right? Fair enough? Make sense? Yeah? So you will apply that to the sinusoid and see what you get. It should have one frequency component, but how does it look when you draw it out is what the little difference is, right? Sinusoids are always a little bit more complex because sine, when you convert sine into the complex exponential form, it has a j in it. So it just makes things a little bit messier. But we all right on this? If you have any questions, of course, let me know. Okay? Right. So you go on here, and one of the things now, one of the uses of the Fourier transform is that we could solve differential equations as well. You remember the primary purpose of the Laplace transform was to help us to solve LTI differential equations, in that you didn't have to integrate the equation and do integrating factors and the like. Once the equation was able to be translated or transformed, then you could use the properties of the Laplace transform and solve the differential equation. The same thing happens here with the Fourier transform. Once we're dealing with, of course, it can solve any problem that the Laplace transform can solve, but it could also solve problems where you have non-causal inputs, right? So because of the fact that the integral for the Fourier transform starts at minus infinity, whereas the Laplace transform, of course, starts at just before 0. So there's a little bit of a difference. This is why the Laplace transform, you need to do initial conditions. In the case of the Fourier transform, you do not. Right? And if you go back here, of course, you can solve the following differential equation, and from the properties which we did before, the properties of this would be exactly the same as the Laplace transform, except that you don't have the initial conditions. So if you run it, you remember that dy dt, if you take the Fourier transform, you get a j omega y of j omega, right? This is why I said to always kind of get in the habit of writing it as y of j omega instead of what some books tend to do, right? The j omega will remind you that, for instance, when you're taking a derivative, that there's a j omega in front. If you are accustomed writing it like this, there might be a tendency to put omega, y omega, and in which case you're going to get an incorrect answer. All right, so just get into that habit of writing the Fourier transform as y j omega instead of y of omega, and then just applying it to what we had before. The question was here, so this is going to give me a j omega y j omega, right, plus y j omega, and this is going to give me an x j omega. All right, so that's the first part. So you get all the y's on one side, all the x's on the other, and then you go to the table as well and get what x of j omega is. Xt is e to the minus 2t, so you could get what xj omega is. So you go through the steps, group the y's and the x's together, and from the table, you know that e to the minus at going to give you 1 over a plus j omega. And again, this is like the Laplace transform. If you forgot, right, you just is the same 1 over a plus s, but you let s equal to j omega. Remember, there are some exceptions, and it doesn't work for certain signals. So in most cases, we will give you a Laplace, a table of transforms anyway. So you make the substitution here. So x j omega is this now, and then you put it all together, and this is what y j omega is. And how you solve it is the same process as before. Once you have this here, you're going to now to solve this particular equation, you're going to have to separate into partial fractions and then go back to the tables themselves. So you separate it into partial fractions. So this is going to be an a over 1 plus j omega plus something over a b plus something over 2 plus j omega. Excuse me for half a second. Right. So you break it apart and you solve for a and b, however you're accustomed doing, and then you check the table for the inverse Fourier transform, and here's your answer. And of course, you could solve this with the Laplace transform just to prove that the situation is exactly the same. So what you need to do, of course, is to remember all of the things that you hate to remember with the Laplace transform: partial fractions with simple roots, partial fractions with quadratics, a quadratic denominator, partial fractions with repeated roots, and of course the ones with complex roots. And once you get that, then you have to everything else is identical to using the Laplace transform. Yeah, make sense? What about this one? Right. So if I ask you what is the frequency, the Fourier or the frequency transfer function, h j omega of this, it means that xt is delta t, the impulse response, right? We went through that already with the Laplace. So again, what just straight off, this one is easy by inspection, and this is where it's important to keep the j omegas here, because this is going to be 2 j omega squared, right? Y j omega. That j omega squared, right? If you just had the omega squared, for instance, if you forgot, it's going to be totally different because j omega squared is minus 2 omega squared. Okay, so that's a little difference in this case, and you run it through. So if you do this, remember these properties, and you can go and solve for the ht as you would have done for the Laplace transform. I will mention this a little bit too later on again when we talk about in the other class. It's kind of a good thing that maybe I'm having you for both electronics and this, because I'm able to make some connections with when we talk about the like we're discussing in electronics, the filters and filter design and so on, that I could try to make a connection there with some of the stuff that we're doing here in the Fourier transform as well. So you can see where it will actually come in. This will come in a little bit when we talk about second order filters. All right, later on this afternoon on tomorrow. Right, so this is straightforward. Any Any issues here with that? Think it makes sense? Yeah? Makes sense. Good. 2 people. All right, not too bad. Right. So somewhat, okay, 2 and a somewhat. All right. So we've watched something so far. We saw that when we were talking about, and we started talking about this even before we looked at the Fourier transform, that the impulse response of a system give us a transfer function. So in the Laplace domain, we get the transfer function. In the frequency domain, we get a version that we call the Fourier or the frequency transfer function. All right. Okay. The step response in the time domain, you get the transient response. And then we saw when we did second order systems that the step response gave us things like that. You remember things damping, overshoot, and the like. So the other part now is that what is the sinusoidal input as a signal, sorry, a sinusoidal signal to a system give us with respect to omega. That proof is a little bit complex, and you will come across it in, so only the j omega would, that's not, let me get that again, half a second. Only the j omega to the power n, correct, correct. It is exactly like the Laplace transform, right? You remember in the Laplace transform, if you have what do you call it? A d2y dt squared, right? Assume you have no initial conditions. This is s squared ys, right? The same thing with the Fourier transform, except that keep that j omega inside of the bracket, right? So if you have a third order system, for instance, it's going to be j omega cubed, right? Which is going to give you minus j omega cubed when you open up the brackets. All right, so that's very important to keep that bracket around the j omega, and remember that it's y j omega and not y omega. Okay, it's a good reminder. So back to this one, and you're going to run through the proof with Dr. Ramlal in controls next time, because it's an essential requirement to understand why it happens in control systems. The proof is a little bit complex, so I'm not doing it here, right? Because as I said, the context is a little bit different and it's required for control, so I'm not going to address it here. But the question is that if I have GT and GT is LTI, linear time invariant, that is an important thing. It must be linear time invariant. If XT is sine omega t, then what is YT? What is the sort of steady state response of YT? Remember that the system, if the system is LTI, linear time invariant, the system will, the G of j omega of the system will have a magnitude and a phase response. Okay? Well, whether it's LTI or not, it will have a magnitude and a phase response. But for our cases, let's assume LTI because the proof requires that. So any system, you know the system, the Laplace of the system is GS, but the Fourier transform of that, right, which will be G of j omega, well, of course, this is complex, so it must have a magnitude and it must have a phase. When you pass a sinusoid through that, all that an LTI system does is that it takes the input signal, it scales the signal by the magnitude of G of j omega, and it shifts the signal by the phase of G of j omega. So in other words, if the sine going in, right, so this is going in, what is going to come out, right, will be sine okay, the magnitude of the sinusoid coming out would change depending on the magnitude of j omega, and the phase, in other words, this little difference where it was from where it is coming out, will only depend on the phase of j omega as well. No new signals, no right? No new frequencies are created at all. That is the linear, that is part of the linear part of it, right? So once you have, and this is great for us, right? Once we make the assumption, and there are many systems that we could make linear time invariant, right? That if you put a sinusoid in, you're going to get, so if I put 100 hertz sinusoid coming in, then what is going to come out of that signal, of that system, sorry, that LTI system, is going to be 100 hertz sinusoid, but it's going to be amplified or attenuated, and it's going to be shifted around in phase. But I'm not going to get a 200 hertz signal, I'm not going to get a 500 hertz signal, and so on coming out of it. All right? Which is very important for us, and it also makes that makes the system predictable. Because just think about it, if I were to put a 60 hertz signal into some system, and then coming out of the system, I have 60, I have 100, I have 150, I have 200, all sorts of random other values coming out, how am I going to use that for anything meaningful? Okay? So that's why there's this understanding of this, and I need you to understand it from a conceptual point of view, that a sinusoid going into an LTI system gives me the same frequency sinusoid coming out, but the amplitude could be different, the phase could be different. All right? The proof, I said, will be a little bit later on. It's a little more advanced, but by the time you get to the proof, you would be you would have done the background work already with Mr. Ramlal. Yeah? So very important thing to understand. Right? So a sinusoid to an LTI will not produce any new frequencies. The input is affected by the amplitude and phase of the system. All right? And the system Fourier, the system transfer function, of course, is just, you take the regular GRS and you substitute S equal to J omega, and you have the frequency transfer function. Yeah? Questions? You clear on that? And the proof isn't that complex. It's just a little bit cumbersome. Okay, but didn't want to particularly sort of, what shall I say, complicate matters for us at this point. It's not required for you to know here, but just to understand, the proof will be a little bit later on. All right, so if we are right on that, so what does SS mean? Steady state. Right, you remember when you put an input into a system, you have two responses. All right, when you put an input into a system, you remember you have a transient response and a steady state response. The transient response is how the system itself behaves, and the steady state response, you remember from our analysis, has to do with the signal itself. So this, right, an initial and final value theorem allows you, without having to solve the differential equation, that you could figure out what the system, where the system will start and where the system will end. Right? If you need to figure out what the system is doing between the starting and the ending, then the only way to do that is to solve the differential equation that is controlling it and substitute for various time values. But as you can see, we already have some tools that we know, and this is kind of like a mini revision here. You remember from what you and I have gone through already, we know that the step response for a system if the system is first order, then the step response of the system only gives us rising or decaying exponents. You don't get anything else. A step response to a second order system will give us, without solving the differential equation, you know, it could respond like this, it could respond like this, it could respond like that, depending on the damping of the system, right? And then we also know that when you put a step into the system itself, the resulting, if you look at the Fourier transform or the result, the transform has two parts. The transient response, which is the part that deals with how the system is, the transfer function of the system, and the steady state response, which is the part that deals with the signal alone. And again, you could find out that from the Laplace transform by setting s equal to 0 or s equal to infinity, and you compute the SXS, and that's your initial value and your final value theorem. So you can do a number of things given a transfer function. You could do a number of things without ever having to solve the transfer function. But if you need to find out intermediate values, then you have no choice but to solve the thing, get it back into the time domain, and plug in values of t and to see what it will do at a particular point in time. Yeah? Right, and that's the point that I've been trying to make with the transforms, is that the transforms allow you to figure what the system is doing without necessarily having to solve it in time. You could figure out what it should be doing in time, and you could play around and adjust things without coming back into the time domain, which is the next part of what we're going to talk about today. Yeah? Make sense? Right, so let's go back here. Let's stop sharing this, and we're going to start talking about something that I introduced already for those of you doing the electronics course with me. Some of you all will have come across this if you have done the course signals before. Then you know what we're talking about. But in electronics, we came across it when we were talking about the response of some filters last time. Okay, so and I told you that we'll do it more formally here. So we're going to talk about this, and this is one of the big properties that we make use of in the Fourier transform to allow us to predict what the frequency response of a system should be without having to go back in time and or solve the thing in frequency and plug in values of omega and see what the magnitude of the response looks like. Right? So if you have a system here, so I am giving you a transfer function here, however it came about, and I want to figure out, well, what is the magnitude versus frequency response of this, and what is the phase versus frequency response for this? So, I mean, you could do it the hard way or you could do it the easy way. The first thing that we do is, of course, if I'm asking you, let me go back here, to figure out what is the frequency response for this, then you know you're talking about the frequency domain. So somewhere along the road, I'm going to take S and I'm going to replace it with j omega. Right? Remember the j inside of here. So the approach that we take now, we substitute S equal to j omega in here. Easier to do if you get rid of all of the higher powered factors. So the first thing that you do, if you're given a quadratic like this, try to factorize it, right? So because I could have just done it here, and if I were to substitute S equal to j omega, just as it is here, I would have 40 j omega over j omega squared plus 14 j omega plus 40. It's 40, right? I wrote over my own writing. But then I need to factorize something afterwards, which is what we are about. So it's easier to factorize with S than to factorize j omega all squared. So if you're given the transfer function, factorize it first if you can. That's step one. So if you factorize it and then make the substitution, this is what j omega is going to be. And then we're going to do something now, which is to draw something called an asymptotic Bode, pronounce it all sorts of ways, but down in our neck of the woods, everybody in campus and everybody who's ever done control systems and signals calls it Bode, right? I'm not too sure how Henry himself pronounced it. He was, the name is Dutch, so I think it's Bode. I believe I've heard somewhere else. But anyway, so once you have the response down to this point, of course, I could, the sort of hard and fast way for this now is to pick a set of values for this, starting omega equal to naught, which is DC, and I could go plug omega equal to 10, omega equal to 100, omega equal 200, 500, etc., etc. And every time I do that in here, plot the magnitude, because if I plot omega in there, this is a complex number, so I'm going to have to plot the magnitude of j omega, work out that, and then on the complex number now work out the argument of it, so I get a phase, right? Yeah, you could do that. That's fine if you have time, or you could use MATLAB and so on, for instance. Or what he came up with was a way of sketching the frequency response. And that sketch allows us, again, like we've said, in using the Laplace transform and in using all the transforms, you want to go from a zone where it is easy, sorry, where the manipulation is tedious or time consuming. You use the transforms to carry you from that universe into another universe where the manipulation is easy, it's just arithmetic, or in this case, is going to be drawing lines. And depending on how the lines intersect and connect, you're going to be able to see in a general form how the response in frequency of the system is going to be, right? So out of this thing, Henry Bode, he was a telecommunications engineer, and telecoms people, of course, are always greatly interested in the frequency response of systems, the bandwidth of systems. So you can imagine if you're dealing with things that go from very low frequencies to very high frequencies, how tedious it would be if you have to go back to something like this and plug in all those omega values to see, because they really don't know what the response is going to be. You're going to have to go from very low to very high, and every time you calculate, you're dealing with a complex answer. So he came up with this thing, and out of his plot, out of his technique, you get two plots. You get a magnitude plot, which is the gain plot, and then you get a phase plot. And these are the sort of what we're going through here, and already you met some of those last time in filters, is that you're going to come up with asymptotic plots, which are, this is just another word for straight line. Right, so straight line frequency response plots. The other thing is that the magnitude plot is plotted on a log scale. The amplitude of the y-axis is in decibels, right? And we saw a decibel is 20 log to the base 10 of a value. Okay? Really and truly, the value is, this is really supposed to be technically a ratio, right? But if you want it technically v, whatever the value is, over 1, and log of 1 is 0 when you simplify it out. So it doesn't complicate matters. But the decibel, to convert a raw number to a decibel, is 20 log to the base 10. That particular base 10 thing cost me about 2 days of work. There was some work I was doing when I was studying, and I had to convert the values to decibels, and like yourselves, they gave me MATLAB to work with. and the MATLAB answer kept being, when I calculated with a calculator, getting one thing, and the MATLAB answer kept giving me the wrong values all the time, until I realized after 2 days of trying to figure it out, that at that point in time, if I wrote log, the log function in MATLAB, this was giving me the log to the base e, whereas it's supposed to be log to the base 10. Right? They've clarified it now. So you I think you have a log 10 and so on in MATLAB. So you have to be careful what you're doing in it. And these are the kind of things that could give you headaches and nightmares. So you know your calculator telling you one thing, MATLAB telling you the other thing, and you can't figure it out. But eventually it dawned on me, right, that it was doing it to the wrong base. Right? So these things happen. So the first thing is tears, literally, right? So the magnitude, the amplitude is in decibels, and then, as we discussed before, the frequency range is also a log frequency range, right? Which means it's in powers of 10. So if you look at it here, this is 1, this is 10, this is 100, this is 1,000, 10,000. We could go all the way up. The business about it is that being a log scale, we can compress, as you see right here, you can compress, in this case, 10 kilohertz into a fairly small diagram. All right, it is for illustration purposes. So the actual, in many cases, you're not concerned, like if they value, if you look at these values here on the graph, you're going to see, like, for instance, this is 1K, this is 2K here. All right, so you can estimate 1500, 1.5K will be somewhere in the middle here. As I go on a little thing, 2, this is 2 here, this is 3, this is 4, and so on. It starts to get a little more compressed. So like when you reach, if I want you to, on this graph, for instance, that you had 8K, for instance, to plot, it's going to be a little bit, sorry, not even 8K. If you had something like 7.5K, you can't really distinguish between 7 and 8K here. So it isn't intended to be like that, right? And what you would do is, if you draw whatever it is, that you would indicate a particular frequency point that you can't really pick off of the axis, all right? But the idea is to be indicative, to show you what is expected rather than plotting exact values. And the same thing goes for the phase plot. The phase angle here is in degrees. So they plot it, it starts the middle, so it goes plus and minus, and it increments depending. And they use the same frequency axis, the same log frequency axis, because typically what they do with the Bode plot is that you have the two diagrams, one on top of the other, right? So you have the magnitude plot on top, and you have the phase plot below, but they share the same frequency response, frequency axis, sorry. So that once you see a frequency behavior in the phase plot, you could just go straight upstairs and you could see what the magnitude at that frequency is looking like. Yeah? Just some simple rules here. So decibels and log magnitude scales. All right, and that decibel thing is actually going to make it easy for us to do certain things as we go along. All right, so just quickly, we have a shorter while we can knock off this here. If HS, if the frequency, sorry, a system has a constant transfer function, so HS is a constant, 2, 100, 75, that kind of thing, right? What is the magnitude versus frequency? Well, of course, this is not frequency dependent, so that the magnitude of the frequency response for it is going to be a constant, right? Whatever that value is, the magnitude of K. It's a number, so the omega is just going to be a constant, right? And the phase, of course, if the constant is positive, the phase is 0. If the constant is negative, negative is minus 180 degrees. In terms of degrees, is the opposite direction. So if HS is a constant, then the Bode plot, as you see, you transform it into the log scale in decibels. So if h j omega is a constant k, then it's going to be 20 log a k, whatever that happens to be in decibels. So you plot it out, and this is what the magnitude plot is going to look like. A constant for all frequencies, because that's what the HS is. And the phase, if k is positive, then the phase plot is 0 for all frequencies. And if k happens to be negative, then the the phase plot is going to be minus 180 degrees. Yeah? Then the other one, which is kind of where we introduced this in filters before, what about a system that has a pole at the origin? So our transfer function looks like k over s. So this particular transfer function, if you plot it on the s plane, this is a pole at s equal to 0. No imaginary parts, no real parts. It's right at 0. So what is the magnitude and phase response? Well, the first thing, you plug s equal to j omega into it, so that the magnitude is going to be the magnitude the magnitude response is going to be the magnitude of this, right? Which is, if you look at that as a complex number, 1 over j, so the magnitude of that is k over omega, and the phase is minus j, which is minus 90. So look at this bit here, right? And that'll be the last thing that we'll look at today. If I take this bit, which is the magnitude plot, convert that to decibels, it's 20 log k over omega is 10 k over omega, right? Which is 20 log k minus 20 log omega. Yeah? So if you put that now on a line, put that on my, on my log scale, 20 log k minus 20 log omega. Well, let's take some points at that point so we can see what it is. If omega is 1, when omega is 1, 20 log of 1 is 0, right? So when omega is 1, the line is at 20 log k. When omega is equal to k, then the line crosses 0, right? So that the line goes like this. And at any point in here, that point is 20 log, well, this is a shorthand, 20 log k over omega. And what is the slope? We did that little derivation by looking at an actual response in the what do you call it, in the when we're talking about filters, right? But let's derive it here. We said we would prove it formally. If you look at this now, right? When omega is 1, 8 omega is 20 log k. That was here, right? So when omega is 1, the magnitude of h omega is 20 log k. When omega is 10, let's go up here now. When omega is 10, then the slope is 20 log k minus 20. All right, because if omega is 10, here, this will be 20 log k minus 20 log of 10, which is, well, log of 10 is 1. So that's going to be 20 log 10 minus 20. So this point, if we were just to substitute and call this 10 for argument's sake, then this is 20 log k minus 20. So in other words, over this change here, this dropped by minus 20 decibels. And we said that a change of a frequency of 10, a multiple of 10. So 1 to 10 is what we call a decade. One frequency is 10 times the other. Then the next decade up would be 100. So you could see why we plot the log. By using our log scale, we could plot in decades very easily. So that a single pole at the origin, the frequency response decreases at minus 20 decibels per decade. Yeah? Right here. So a single frequency, a single pole at the origin, the gradient, the frequency response, as you crank up the frequency, it decreases at 20 dB per decade. A single pole, for instance, is a capacitor. So if I have a capacitor, who has a big capacitor? But if I have a capacitor and I have a signal going through the capacitor here, and you're looking at the voltage across here, we saw already at DC at very low frequencies, the capacitor is largely an open circuit, so that the voltage here is going to be whatever is that source. As the frequency starts to crank up, the capacitor slowly starts to short circuit the voltage, because the impedance of the capacitor decreases as frequency goes up, so that this voltage now is going to progressively short, and the voltage here is going to get less and less. Well, as we're seeing in the frequency domain, that response is going to look like this. It's going to decrease. So as the frequency goes up, the magnitude of the response, right, is going to drop. And it's going to drop at 20 dB per decade. It looks nice and linear. When you draw the log scale, everything is a nice linear slope. We know in the time domain that the response is an exponential kind of decrease. All right. And what about the phase? Well, the phase response, so the magnitude response is going to look like that. What about a phase? Well, Hj omega is minus, remember, it is K over J omega. So the phase is a minus J, which is minus 90 degrees. So that a pole at the origin, the frequency response decreases in the log scale at a minus 20 dB per decade, linearly all the way down, and the phase is minus 90. So it's always minus 90 degrees out of phase with whatever signal was driving it. Yeah? Fair enough? So any questions before we close off here? Right, so you understand the concept, what we're doing. So just quickly again, you notice what has happened. You're given Hs is equal to K over S. The question was, what is the frequency response of that? Well, yeah, I could go and I could find the inverse thing and plot it in time versus frequency and all that kind of thing, right? Or I could plug S equal to J omega here, and I could plug in all the omegas and so on. But we're now seeing that something like a single pole at the origin, that the frequency response now is a linear, well, this axis didn't plot good, but it's a linear frequency response. It starts high at close to DC, and it continues decreasing all the way down as you increase the frequency. And that the phase is now a constant minus 90 degrees. Right, so that you have a behavior here without solving the thing. Here's a line that is showing me, so I could get a visualization now that as the frequency goes up, the magnitude of that response is going to drop. All right. So we'll continue this as we go forward, because we have all other combinations up to and including quadratic responses to look at as we go forward. All right. So look over the notes and listen to this when you get a chance. And tomorrow, please God, we will continue with this. All right.